Hi everybody, and welcome to Intel Architecture All Access Season 4, Graphics on the Go. My name is Tom Petersen, and I'm an Intel Fellow and a longtime graphics guy. And today we're going to deep dive into the brand new Xe2 architecture, which is inside our Intel Core Ultra processor, codenamed Lunar Lake. I remember my first experience with graphics was in Austin, Texas in the 1990s, and I was playing a new game called Descent. It was the first time I had seen real-time rendered 3D anything. And it was a first-person space shooter. But it was before GPUs, so everything was being run on the CPU. And that means that the resolution was a little bit smaller and the quality was a little bit lower. But yet, the experience was so good, I was still hooked. Since then, GPUs have been invented, and GPUs dramatically accelerate the computation of images for gaming and for everything else. GPUs started off with gaming, but today they do video encoding, they do decoding, they do all kinds of content creation, and they also do computation. Things like AI are primarily driven by GPUs. And those GPUs can be found everywhere. They're in your laptops, they're in your desktops, and they're even in your phone. Of course, GPUs have evolved over the years. We've added more capable fixed function blocks, and the programmable blocks in the center that do computation are now used for things like AI and other applications. So the GPU has evolved to become much more power efficient and generally programmable. Gaming workloads are changing dramatically, and that's what's driving the change in GPUs. Games used to run at really low resolution with low fidelity. Now they're much higher resolution with things like ray tracing and complex dynamic scenes. All of this at the same time demanding higher frame rates. Higher frame rates drive the experience. As frame rates get higher, immersion gets better, and the games get smoother, and the latency gets shorter. So higher frame rates are just as important as quality frames. This all comes together through a process called rendering. Now, rendering begins when a 3D artist creates a mesh, and those meshes might be goblins or trees or witches, and that's given to the GPU and the GPU driver, and it converts it to a two-dimensional representation of pixels that you see on your screen. That process, called rasterization, has lots of tips and tricks and techniques to allow that to happen using reprojection. There's a different way to render images called ray tracing. There's no reprojection in this case, and instead, there's a physically accurate simulation of how light interacts in the scene. You need lots of rays to get good results, and sometimes you can have performance challenges. The good news is that there are techniques to use ray tracing in real time, and it's called hybrid rendering. In this case, we use rasterization to generate what we think of as a base image, and you use ray tracing to make it look better, things like shadows and reflections and global illumination. When we're dealing with this hybrid rendering, we really need to look inside of a frame. In this picture, on the left-hand side, we're doing rasterization, where we're taking those three-dimensional models, we're doing the reprojection, and we're actually generating the first pass of pixels. In the middle part, we're using our ray tracing engine to sort of interrogate that scene and generate things like reflections and shadows. And in the last part, we're using our XeSS technology, using an AI algorithm to upsample the entire image and generate what you see on the screen. To implement all the steps required by that pipeline, we have three main functions. First, there's a bunch of fixed function logic that does things to help accelerate the generation of pixel. Secondly, we have a bunch of programmable logic that we call Xe cores, and that's where the bulk of our work happens. And lastly, we have a bunch of software that ties it all together. When we're developing new GPUs for all of these different functions, we start by looking at workloads. And that's often new games or new features or new APIs. They're constantly changing. We also look at our existing designs to identify things that we can improve, things like stalls or bottlenecks. And lastly, and most importantly, we spend a lot of time talking to developers. So we're always working with the next game engines or the next games to make sure our new innovations are easily adopted by the ecosystem. For Xe2, that analysis resulted in changes all across our design. It started with the Xe core, where we added support for SIMD16. SIMD16 will improve game compatibility across the board and give a general performance lift to most shaders. We've also improved the front end and the back end of our 3D pipeline. On the front end, it's all about geometry, where we've improved vertex fetch significantly. On the back end, we've improved our pixel blend rate dramatically. For XE2, we've also improved our ray tracing. We now have 3 traversal pipelines for up to 3x throughput. And we also do 2 ray triangle intersections per clock for up to 2x the throughput at the final leaf. We've also made changes to better support AI in XE2. Now, all of our variations of XE2 include support for our XMX array. Now that XMX array enables 4,096 int8 operations per clock. We also support int4, BF16, and FP16. One of the most exciting things for me is that these AI technologies directly apply to gaming. We use them in our own technology called XeSS. XeSS is an AI-based technique where we take a low-resolution image and then we use AI to scale it up to higher quality, and we can do this at higher performance and lower power than we otherwise would have been able to with normal raster. All of this technology will first become available in our new Intel Core Ultra processor, codenamed Lunar Lake. The goals of that project are aggressive. We need to bring down power, scale power down, but at the same time, raise performance for graphics, which means we need a more efficient core, and that's what XE2 delivers. For Lunar Lake to deliver the efficiency, we've built a big, wide GPU. That gives us great efficiency. Inside that GPU, you'll see 8 Xe cores, 8 megabytes of dedicated L2, 64 XMX units, all together delivering great performance at great efficiency. We also have a dedicated media block and display block that also run hyper-efficient. For Lunar Lake, we've also improved XeSS. We have new kernels which are hyper-optimized for that architecture. It's optimized for XE2 and XMX. We also use a smaller model in our neural network, which we call XeSS Lite, and that gives great performance and power efficiency. XeSS adoption is going great. Already we have more than 100 games adopting XeSS. It's easy to integrate, and to be fair, gamers are missing out today if they don't have that technology. At the end of the day, all this work in the brand new XE2 architecture and Lunar Lake, you're going to get a great gaming experience. All of your games are just going to work right out of the box, and you're going to see a 25% performance uplift gen on gen. Not only that, some titles are going to be up to 50% faster, and you're going to see a significant win over our closest competition. We deliver this performance with great efficiency. XeSS technology makes it even better, delivering between 30 and 60% performance improvement using our AI-based supersampling technology. Altogether, this is the most power-efficient gaming experience ever on a PC. I'm really excited by all the great designs and form factors coming from all of our partners, and I hope you enjoy them. Now, as you know, XE2 is our new architecture appearing first in our new Core Ultra processors, codenamed Lunar Lake. But that's just the beginning. Stay tuned, Battlemage is next.